Censorship evasion. Automatic algorithms for evading, circumventing automatic censorship systems. So it's going to be more of a relaxed paper discussion because I didn't prepare anything like a presentation or something. Just one paper, like simple, a relatively simple topic.
It doesn't sound simple.
I mean, it's simple as compared to a survey of all 3D storage and compression techniques
Yes.
ever.
It's not on.
And so, like, for context, the plan is this talk, discussion, then break, then the last talk about CPU bugs.
Which one do I need to plug in?
I think this one worked for me.
Oh, it should work. Yeah. Because I'll probably try to use a whiteboard. Okay, so the topic of today's discussion is Geneva, evolving censorship evasion strategies. Geneva is literally genetic evasion. Genetic evasion. So, TLDR, like a very short description of the idea that I'll just go over here, is that there's automatic censorship systems. They try to look at your TCP packets and block forbidden domain names or keywords. But what you can do is somehow modify your packets so that they aren't blocked, and there's a genetic algorithm that picks these actions such that your packets are not blocked. And this is a whole paper about that. It's open sourced. It's from 2019. There's a GitHub repo with the code. There's some research stemming from this using like neural networks and with reinforcement learning to do the same thing. But this is like the basic approach that I think it's good to discuss, particularly this one.
Is it currently used in the wild?
I honestly don't know. So before looking at this paper just randomly because of something at work, I did not learn anything about censorship systems. I still don't know basically anything about censorship or networks or I don't know, TCP. So it's like very intro. Maybe some of you know more about networks than me. But I'm pretty sure. So this overcame China's automatic censorship systems and some others. I'm pretty sure like some people probably use it.
Sorry, can you make it a little bit bigger the right side?
On the right side so they can see anything. Yeah, sure.
Yeah, yes, because we don't see. It's too small, okay? Yeah.
Yeah, then I'll just zoom into one column.
Okay.
But do you need notepad?
What do you mean by notepad? I wanted to. Yeah, let's just. I just want to use the whiteboard sometimes. Let's delete this. Okay.
Oh, nice.
So, who here knows what? Who here knows what a genetic algorithm is? Hey. Who knows what reinforcement learning is? So some people. Okay. So, who does not know reinforcement learning and genetic algorithms, but knows gradient descent or neural network training? Okay, whatever. Point is, here's a system. There's a sensor, like the guys that want to block our messages. It's basically a classifier, like a sensor of a message, a packet, whatever. It's either one, like forbidden data, forbidden messages, and it should be blocked, or zero. It's okay, we can pass it on, we can leave the people alone and not bother them. So this is like a classifier that processes each of our packets and checks whether it's bad or not. And usually, and in this case, and when we're in the wild, we don't know how the sensor operates. We don't know what this function is, and whether it's some kind of a neural network or a handmade chain of if-elses. We know that we can just give it messages and get back whether the system blocked it or let it pass on. So the difference from a typical, for example, neural network training or like any kind of optimization algorithm is that we can't do gradient descent with this. We don't know the implementation of this. If we, for example, do some kind of generator, I don't know, like a modify function of a message produces a change message and passes it to the sensor. If this sensor was like some kind of neural network or any other system that we know how it works, we can somehow optimize our modifier because we know how the sensor works. And this way, like, find the optimal modifications we need to do to the message. But because we don't know anything about the sensor, we need to like do this optimization in the wild. When we don't know how it's implemented, we just throw it messages, see whether it was blocked or not, and depending on whether it was blocked or not, we say that, like, okay, this modification works, this modification to the packet doesn't work. So for example, we can, I don't know, send a message, it's blocked, and then send a message but reverse every single word, and then it's not blocked, and the receiver on the other end can decipher the message back. So this is like a modification that would work. And so we can cycle through these ideas until something works. So what I'm talking about is like something that's called zero order optimization. Probably Sasha likes this term a lot. He likes to use words like first order, second order optimization. So like we don't have gradients, we don't have second order gradients, we just know the results. And for reinforcement learning, if you know what reinforcement learning is, we again have like some kind of system. For example, we train a bot to play Atari, and even though we know how Atari works, but what we do is just we have a bot. It performs some actions, and we, depending on the output of the game, we can say, okay, you performed bad or you performed well, and so on. We can train the bot to perform well always. But here we use a genetic algorithm that is an evolutionary thing. So the idea is we have like many agents. So for example, this agent has algorithm 1. Agent, I mean like just instances of an algorithm. Algorithm 2, algorithm 3, algorithm 4. Each of these are different algorithms, and we can throw them to the sensor or to our system. Like there's a system. Like throw all these algorithms into the system and get like rewards or like successes. This algorithm gets reward 1, reward 2, reward 3, and so on, right? And so the one that gets the highest reward survives. The ones that get lower rewards, they either die out or they have to like compete. So the idea is we have like hundreds of these algorithms, and we have some reward function that tells whether this algorithm succeeds. And we want the algorithms who succeed to survive and create offsprings of these algorithms, like variations that will likely succeed. That is one of the next ideas. I want to show actually a video I remembered, like genetic algorithm racing. Like I think something like that. Yeah. So like they basically made a neural network that implements like this bot for racing, and they launched hundreds of these cars to race. Generation 1, it's hopeless. Some cars perform somehow. Some cars don't ride at all. So the reward function is obviously like how far your car has gotten.
One is literally dragging One is literally so good.
Yeah, so one is lucky. Like this is the strongest offspring in this generation. And so we will definitely choose it for the next generation. And it will generate variations of that algorithm, and so we do this for multiple stages, where we choose the best algorithms and do offsprings of them, and so on and so on, and generation 7, it's already a lot better, and so on. So this is how most of the times bots for games are trained. You run thousands or hundreds of these versions of these bots. You have a reward function that tells the bot it performed well. And then if the bots that performed the best, you mix their algorithms somehow, mutate them or something, and so on. You get better and better bots.
Nice graphics.
It's how it called
TrackMania or something, yeah. I think.
yes, Mania, yes.
Oh yeah, TrackMania. So I think it's a game specific, not specifically made, but there's a good framework for bot training and stuff like that. So yeah, that's the basic idea of genetic algorithms. Where is it? Yeah. And we can do the same with the censorship systems, where we have algorithms for modifying packets. We have a system that censors, and the reward function is if you're not blocked, it's a high reward. If you're blocked, it's a low reward. So these algorithms will evolve until one of them isn't blocked ever. So
what are our particular building blocks here?
yes, so this is the general idea. Now the building blocks. So what are our algorithms? What are they built of? How are they mixed, mutating? What do we initialize with? So the Geneva's building blocks, literally, what do we build our algorithms of? They look like this, just like for first visual. An algorithm looks, for example, like this, but this is just a visual for comparison. The idea is we have triggers. So TCP packets are somewhat like dictionaries. We have a TCP packet. TCP packet. It's it consists of a flag. So it's either a start of a handshake. So for example, if it's start of a handshake, I think it's something like SYN or ACK, something like that. Then we have a checksum. Checksum. We have the payload, the message itself. Then we have offset. If it's one of a series of packets, and so we need to provide offset which particular packet it is, and so on. There's lots of fields here, and so and so. A trigger is something that operates if a particular field equals a particular value. So it's just an event trigger, right? As in games, as in whatever, you have an event trigger. And so if this trigger triggers, you have actions. An action is defined as a tree of actions. So there's these options, and I'll just draw a quick visual for example. A packet can be fragmented into two. So, for example, we have a packet here. One example action tree that we can take for one of the triggers is we fragment it first into two halves. We first this. Let's send this packet. So okay, this is.
Can I interrupt? So they were actually messing with TCP packet, not by a lot of TCP packet. I mean, they basically messed up with TCP packet itself, structure of TCP packet.
Sorry, can you repeat again?
What was they messing up with TCP packet structure itself?
TCP packets, the values of the TCP packets.
Okay.
So the fields. Yeah. So they, for example, we can take a packet, we can fragment it into two, and then for each of those two fragmentations of a packet, they don't fragment the packet itself, they fragment the particular field. The payload, I think, the actual message in the packet. And then that other second half, they can, I don't know, corrupt some field.
No, so they're actually messing up with it.
Yeah, they can mess up some of the fields in the packet.
I'm pretty sure it's raw packets, not only payload.
A particular field of the packet, not an overall bit structure. they can corrupt the payload, they can corrupt the checksum, they can corrupt whatever, and then they send this. So we have a structure like this. These are the actions. We can duplicate it, so we can, instead of fragmentation, we just copy it, do some actions in the copies, and then send those one after the other. Like these action trees, they're very flexible. We can, in the end, come out with, I don't know, like 50 copies of the same packet, and maybe that's something that we need to do in order to bypass a censor.
So I just like to
Yeah.
To go with this maybe one time. So like the entire set of actions we can take. Like so, we have a raw packet, as a packet, all its fields, and the entire set of actions is duplicate, fragment, replace or corrupt, and drop and send.
Yes.
Okay.
And we construct a tree out of those, like an action tree.
Yeah.
What's on the other side? Who receives packets or not? So they send packets, but does the receiver do something?
Oh, so yeah, that's actually something that confused me too. So, for example, we fragment the packets. Does that mean?
I mean, we can send some random shit and it works.
Yeah. So when we look at how the reward function works, in theory, we can just the first action we do is drop the packet and that's it. But then we can't consider that a success. So the reward function is actually we are not blocked and the receiver got what we want. So this is the reward function.
So does this thing need the other side to run this into? Or
No, so the other side does not need to think about what we run.
okay.
Apparently, also we can fragment our message and TCP/IP stack the protocol.
We reconstruct it back.
It can reconstruct it. So there's like inside of the protocol, there's stuff for reconstructing like a fragmented message. So we don't need to like inform our receiver that we are doing this smart shit.
If sensor just recreating everything properly, so it will block it.
The thing is, the sensor doesn't do that. So like, but if yes.
So for context, like how the sensor works. First of all, the sensor wants to track everything in the country, right? And so they don't have enough resources to do. For example, this paper mentions that in theory they could refragment all the messages back, do all these sort of processing for the message, try to decipher or process it with a smart neural network, but they don't have the resources to do that for everything. So they try to do the best with the resources that they can for every message.
But technically, they can just choose whom to track.
Yeah, of course, they have like a blacklist.
Like we see that some guy is doing something interesting, let's track him better.
Yeah, so of course they have a blacklist of IPs. If they notice that once you address the domain name that is forbidden,
No, I just mean technically they can just check abnormal stuff and see like something abnormal. Or let's just figure out what deep is it, what key is it.
that is true, but that's not the coverage of this paper. So the coverage of this paper is that they don't have attack man in the middle. So like a typical like when you learn cybersecurity, like cryptography and stuff, you have like Alice. They somehow connect through something to Bob. There's a message, goes through these like servers in the middle, and then it comes to Bob, right? So, and then in the middle attack is when one of these servers through which the message passes is the attacker, so bad guy. And so in theory, what he can do is replace your message completely. So he can see your message and replace it. So Alice sends a hey, and Bob receives I don't know, I'm against this government, or I'm a traitor, I don't know, or just stop the message. What this does, so they don't have resources to have, I don't know, all of the ISPs install this and do this. What they do is ask the ISPs to send them copies of each packet. And so this is, for example, the ISP. The ISP sends to the government, and this ISP and this ISP sends to the government all of the packets, and the government looks at the copies of the packets, and then if they deem it forbidden, they can't change the message again, right? So the message already is passed on further, but they can inject a new message into this connection.
They can do what? Can't.
So they can't replace the messages.
They can replace, but they can inject.
But they can inject.
What's the difference?
So, for example, when you do TCP handshake, so there's again Alice Bob, you have like hey, TCP hey, TCP A1, TCP, are you sure, and stuff like that. So TCP has like 3 back and forths to make sure that you have a connection. And somewhere in the middle here, if they somehow notice that this is actually a forbidden domain, they can, from the side, say, okay, end connection. Pretend that they are Bob, say end connection, and then Alice sees that, oh, Bob end connection. Okay.
Yeah, so the difference, they can't replace what you already sent because it's already sent over, but they can add this new message because
The
it's
message is breaking channel.
no, a message which literally says bye bye.
There is no messages, there is no just connection.
No, that's a different thing. I mean, they do not have state. That's important. Like they try to minimize the operational resources, so they do not implement a stateful firewall. What they do is they track that you connected. So like you got a TCP SYN, and like if TCP SYN, so like no state, no look ahead, no look back. If TCP SYN, then send TCP disconnect.
Something like that. Actually, they have some kind of like state, but they keep a very limited state of a particular connection. But yeah, this is what they try to do. Okay, so this is like for context. They can't replace your message, but they can try to inject something. This is the action that they take, and one of the examples they provide for their algorithm for modification. So, for example, if the packet is SYN, so S here stands for SYN, I think it's like the beginning of a TCP handshake. If it's the beginning of the TCP handshake, we duplicate the packet. First version we like replace with a different flag, SYN ACK. It's something like another part of a TCP handshake initialization. The other copy we send. And then if it's reset block, which is the end of the connection, they drop the packet. So I think this is the more important thing. So when we initialize our handshake, we duplicate the packet. One of the packets we actually send the wrong flag, and the other we send as it is. So this is like an example. The thing is, we will see something similar in the stuff that works against China, something very similar, and there's like logic behind why that breaks China's firewall.
Also, I think like the important thing here is that this like OR operator, so like the what?
This one.
This one. What it says is that the uppermost part is what we do on outbound packets, and the downmost part is what we do on inbound packets. So what this strategy here does is it drops incoming packages which say that the connection ended.
By the way, I myself didn't fully understand this part. Do you understand why they drop the packets? What they care about is for their outbound message not to be blocked, why they do need to process inbound messages.
I have no idea.
Yeah, so they do mention that like the second part with the drop is for...
No, actually I kind of do. I mean, I think that has to do with TCP being stateful. As in, if our objective function is, say, the number of bytes transmitted or number of outbound packets transmitted, then like TCP is not a dump pipe because we have this like SYN ACK dance, connection establishment dance, and so exactly as you said, if at some point we get an end connection packet, then the pipe drops and we can't send any more outbound packets. So like our objective function is limited by that bound. And so if we never drop the connection, then we can then our objective function can go on.
Okay, I get it. So yeah, we can prevent the TCP connection from dropping, and this way, like, lie to our the sensor will see that okay, we received the end connection packet, so we should stop tracking them. But in truth, before receiving this packet, we drop it, so we actually continue the connection.
Yeah, exactly.
Okay, so now for the so they talk about how these building blocks can basically build anything that previous works do. And now for the evolution. So they initialize the population of their evolution with 200 algorithms, each with random but valid action trees, precisely 3 actions, stuff like that. So it's not interesting what they start with. The interesting part is how they mutate. So the mutation. Mutation happens when we select the best algorithms, but instead of like always sticking to the best algorithms, we need to make variations in them. So that the variations are called mutations. So how do we can mutate algorithms? So if we have a duplicate action, we can randomly swap the trees, the action trees on each of the packets. If we have fragmentations, again, we can like shift the fragmentation offset or change the order. If we have temper, we can randomly change it to replace or corrupt. If we have drop, we don't change it. And so then we have like, this is interesting, I think, isn't interesting. So they can combine trees. Also, no, combination is crossover. Sorry. To mutate an action tree, one over four primitives. So I don't think it's very interesting to discuss like the probabilities of each of these different ways to mutate an algorithm. But basically, they have various ways of mutating these action trees and triggers. Then.
What is that about drawing from real packet captures?
Okay,
the last paragraph.
Let's go for this one. Strategy.
Yeah, actually, it's. The last sentence in the previous paragraph. During mutation, actions and triggers are given access to the packet capture of their previous run, so they can take mutation values from a real run.
Again, what do you mean? Sorry.
A mutation ought to change the values to a particular new value, and we could just sample a random one. But considering like the state space, a random one is likely to be just a corrupt packet. And so what they do is they give the system a packet trace of the previous run of the system, so that it has a sample of real packets and some real values to choose from too. Yeah.
Okay, so they mutate with a bias towards something they can see in the real world. Yeah. Okay, and for crossover, it's a kind of breeding of two algorithms. When we have two strongest, we may want to see what will happen if we like somehow combine the two algorithms. Just at random. Trees are randomly swapped, trees are randomly mated, so we can like combine two binary trees by mixing their children and stuff like that. Again, this is not interesting. This is like specifics of the particular genetic algorithm. The interesting part is, so the reward function I think is more interesting. So, evaluate a given strategy. Positive numerical fitness metric if the connection could properly finish. So again, like the connection will not properly finish if we are either blocked somehow, or if like our strategy just drop the packet, or corrupt the checksum, so the packets are never confirmed to be valid. And there are additional adjustments. So also sensors sometimes fail to block negative content, so they run a particular algorithm against the sensor twice to make sure that the sensor catches bad messages and takes the worst fitness score, the worst reward. Then they punish actions with triggers that never trigger. They punish actions with the number of packets. So as I said, in theory, this action tree can produce like 50 packets, and they like assign less reward if you have like too many packets on the output. And finally, strategy complexity. So they reward strategies with less actions in the tree. And so they say later that first, like strategies evolve into these complex monsters, but which work. And then using these like punishments, they converge to something that works, but also is pretty short and concise and nice. And this is like the description of the genetic algorithm where we choose, mutate, combine, and go again.
Yeah, didn't they consider kind of manually, in the sense that automatically you just write an algorithm that shrinks the trees?
Or you're
Drawing,
like
way kind of necessary actions because like, when we have this tree, then the strategy we can unexpectedly see what it does and we can.
They didn't write
simplify
about this, but they did say that like in the first stage of every adaptation to a new sensor, like in the beginning, all these useless branches in the trees drop off.
I think what's actually asking if they did it statically, and you are saying that they did it dynamically.
They didn't do any kind of manual modifications. They didn't. As I hear, my understanding of your question is that do we process the trees to do some kind of compression of the trees because we can get rid of useless branches, for example, right?
I think it's more like if you have if your tree goes like change to A and then change to B, then you can compress the stats.
In theory, you can do that, but yeah, they don't do something like that here. They just the genetic algorithm works. It determines when we can just get rid of these operations, or in theory.
If you do kind of manually this thing, that algorithmic, you can compare and see if it converges faster.
Yeah, true.
Efficiently search through the search space and stuff like that. Anyway, we're kind of manually changing the trees because we're mutating them and making crossovers.
I say
at the same time, we can shrink them. Like, why not?
Arguably, the key insight is that they are very efficient as they are, which is surprising to me at least.
I don't know. Well, we didn't cut to the metrics. I don't know how efficient.
So I don't remember how fast they are for China, but they did say that for Kazakhstan to break their automatic censorship systems, it took them like 15 minutes to come up with an algorithm that consistently, like 97%, surpasses the Kazakhstan censorship. For China, I think it took like a few days probably. Let's go to the metrics.
Feels there is still room for improvement.
I don't understand what you're asking about shrinking. What are you trying to shrink?
Dino provided a good example. So, for example, if we have an action to change the payload to a string A, and then the action after that to change the payload to string B, we could replace that with just an action to replace with a B, right? Yeah, so we can do operations like that for different kinds of actions.
So
Or if we do like
kind of simplifying.
yeah, if we have two corrupt operations one after the other, we can replace them with one corrupt operation. So in theory, we could do that, like compress trees when we can, but they don't do something like this. Yep. So like later in the paper, they say that what? This is just implementation details, so it's Python 6,000 lines, open source. Let's look at how it works. Finds working strategy in all experiments. They say that our algorithm works, but if we just generate random strategies, it won't work. So our thing actually works in finding new, or not new, but cool working strategies.
What's the actual testing? If you go from China, for example, to YouTube or something, just blocked by IP, what was actually tested? Did they test VPN or something?
They tested by they just know a few forbidden websites and.
If they block by IP, what would that say?
Actually, not sure how they did that.
I mean, if they test some VPN protocol or something, it's understandable. But if they just blocked IP, it's strange.
That's interesting. So.
It can be blocked by keywords and domain name, not just IP
blocked by
side,
IP.
by just not just by IP. It can be blocked on L7 level just by keywords in the domain name.
So what was the?
So in China's the Great Firewall. It's after a client makes a sensor request, the GAW forbids the connections for 90 seconds from between these two IP addresses.
What?
So when you do a request to a forbidden IP address,
Yes.
they block any kind of exchange of packets between you two for 90 seconds.
And why they not block, for example, why So okay, is it, I have a question. I will ask in the end.
I think I have an answer.
Yes, yes.
Okay, so like you make an HTTP request to a website, and
No. I will ask and you will answer. because my question is enough.
No, ask you.
Ah?
You ask?
You want to
I
ask
didn't
something?
ask
Oh.
yet. I will ask later.
Oh.
Okay. So they find 7,917 sites out of the above that were not immediately censored. So they do a search and find websites that are not immediately, for some reason, blocked by
Oh.
China when you request to them. Okay. So we'll have Geneva training against the Great Firewall over 16 days. So it took them 16 days to crack China.
Mm.
For Kazakhstan, it will be like 20 minutes or something.
I'm just thinking maybe they should test on the website that some protocols that are not very good for China. So
Yeah, but they fix themselves to like TCP packets only.
yeah, VPN is not TCP.
it can be TCP. Like OpenVPN would be TCP, but WireGuard would be UDP. So like that have to be. And I think it's instructive to take another look at the methodology in China. So like what they're doing is they have a bunch of websites which you can reach, but like I don't know. Say you have Pornhub, and on Pornhub you can either view like introduction to calculus video, or you can view like I don't know hot milf porn video.
But if it's a server.
Sorry?
If it's an encrypted one.
Well, they are doing the evaluation on HTTP only websites. Okay, so like HTTP only websites and
Many of them.
10,000 of them.
Anyway, this great Chinese firewall either decrypts HTTPS or simply forbids it.
Yeah, so there's like
So
stuff called
your communication is unencrypted. Anyway.
there's stuff like deep packet inspection when even when your packets are encrypted. I guess I'm not sure how that works, but deep packet inspection can notice patterns and find that something is forbidden, even though maybe they're not sure why.
Yeah, but that's not what the evaluation
Yeah.
is. Okay, so HTTP websites and a website has both like good and bad content as according to the censor. And if the censor sees a bad request, so like view porn request,
So it's HTTP website, not HTTP.
HTTP website. If they see a bad request, they drop all connections to the IP for 90 seconds.
Yeah.
But if the request is good, they don't. So like what our thing does is to try to make all requests look good.
Mm.
Again, HTTPS is irrelevant in this case.
I'm not sure if Chinese just block all your HTTPS traffic.
Yeah.
Are you sure?
Yeah.
I was in China, I was sitting in Google, it worked.
So
Google Translate.
yeah,
They didn't block my HTTP.
they mentioned that DPI.
They either decrypt HTTPS.
Come on, I was been in China, I used HTTPS websites, it's worked.
Okay, why you think they did not encrypt your traffic? Decrypt your traffic.
So they just took all certificates from everyone,
Yeah.
re-encrypted everything. So
Yeah,
they're
they
so
act as
powerful. It's a very arguable question, and you can just say yes and do that.
Well, I know. I think it's documented that they
The
exactly
document
do
is that
this.
China gets all certificates from everyone in the world and decrypts and decrypts everything.
No, either you use their certificate that can.
No, I didn't put any certificates. No, I mean,
It's not a
wait,
question.
so you say my iPhone was backdoored and the Chinese put certificate in my phone? No. Or I just used all the same certificate from Hello China or something like this. And they just
I
print
don't know, exactly the mechanisms.
I mean, it's very retarded to put, for example, Chinese issue some certificate for Google for everyone, then they put it to your phone, you just download certificates and just state that China do some random shit, just cancel the certificate.
Now, I mean, great question for next time, I suppose.
I mean, what you are stating is very arguable and without proofs, it's not very good idea to state it. And Am I saying
I
something?
think you're talking about some different stuff. I kind of don't see immediately like what was the problem. What are you trying to say that where there is a contradiction?
I just asked if
What
why
the-
so many HTTP websites have HTTPS.
Right. So let's maybe postpone that.
Yes.
Yeah, again, I'm not, I guess, as familiar with people as I could have, and Dima actually, I guess, read it and also knows about the paper a lot.
It's just that I worked on this sort of stuff.
Makes sense. Yeah, so do you want to talk about strategies? So some of the strategies are pretty nice. I won't go over all of them. So these are the algorithms that the genetic algorithm found. Again, as you can see, because of our punishments for long, complicated algorithms, we come up with something that works 98% of the time and is pretty short. So, for example, this particular one is when we have a B8 packet. So, B8 packet is which one? It's push ACK, push ACK. It's acknowledge received data. So yeah, we did receive data. So when we send something about us receiving data, we can say that okay, the offset of whatever payload that we have is actually larger than this. So for example, if we start sending packets, we can say that actually this isn't the first packet. This is the 10th, not packet maybe, but whatever. This is the 10th in our sequence, and also corrupt the checksum. And this is what we send first. So we first send this. The sensor sees this, these two places. The fact that it's with an offset, they try to resynchronize their state. Oh, this is in the first packet, which means we need to synchronize it to something or whatever, and reevaluate what we're actually tracking. And then they see that it's actually corrupted. Then they probably drop their state, saying that okay, this connection will be dropped then. And then we immediately send the actual packet, but the sensor isn't tracking us already. And so this practically works.
That's pretty cool.
Yeah. Then
So what we're essentially doing here is finding bugs in the implementations automatically.
yeah. What else do we do? This is if so again TCP just ACK is what? TCP ACK is acknowledges. Oh, it's receiving a series. So this is specifics. I guess it's almost the same as a push ACK. So duplicate. So first we send a packet. So when we want to send a packet, we first immediately send the packet that we want to send, and then we send it. We actually stop the connection and we tamper with the checksum. So what does this do? The most successful strategy.
That's the other one. That's switch.
Implementation. Swaps two packets. No. This is. It's
again as a strategy to have the sensor drop tracking of the state because what for some reason happens. I'm not sure why. Is that the server ignores the reset, but the firewall sees the reset and acknowledges it as true, and therefore drops tracking.
So yeah. I guess this is a bug. So when we send the packet,
The server ignores it because it's corrupted.
Yeah, so we send the packet to our receiver. The receiver receives the packet, but then to the sensor. Sensor also notices the copy of this packet, but with this is called a reset connection. It's basically stop the connection. So the sensor sees this and thinks, oh, let's stop our tracking because the connection is stopped. But the checksum is corrupted, so our receiver actually sees that the checksum is corrupted and does not think that the connection is stopped. So another
I didn't
bug.
understand in the beginning, but now yeah.
Sure.
Yeah, I was not understanding why the server doesn't need any modification, but now it's more understandable.
Yeah, and here it's a little more complicated. I won't go too far into this. So okay, so about Kazakhstan, where's Kazakhstan? Other countries. Oh, so they have India. I don't remember them saying how long it took them. well, they mentioned Pornhub for something from the sensor side Pornhub, and consider the strategy. See. Oh. So yeah. Oh, they have something that works 100%. So it's replace the length of the packet with 64. Send that packet and then send the initial packet, and that works 100% of the time.
Everywhere.
In India.
In India.
Ah, okay.
So I guess this is like again some kind of bug where if you have a particular length, then the sensor immediately does not consider you bad.
It's not a bug, it's an optimization.
Yeah, it's a feature.
A performance feature.
For Kazakhstan, something was 100% is you send a packet, and then you send also a packet but with the corrupted payload, and this apparently just again confuses the sensor to think that we sent something that does not contain anything forbidden because it's like some random order of strings, and they again drop connection, nothing bad here. So again, they do some interpretation, but we can interpret this ourselves. Yep, and I think they also say that
So you have 2,000 pages.
who has 2,000 pages?
I mean, the page number was 2,000.
No, it's
At the bottom of the page, I think.
the bottom of the page.
11.
Oh, I guess this is from a journal or something.
Session 9. From conference.
From conference. I mean, everything else they say, they like they like some of these algorithms very much resemble previous work. Some of these manage to make some algorithms work that previous work stated these algorithms wouldn't work, and stuff like that. Yeah. Also, like in the beginning, I forgot to mention, they I think it's for reference 21. Yeah, so they mentioned like a genius thing. One of the other papers in this area mentioned one way to avoid a sensor is to send the TTL time to live of the package. So like when you receive this package and the time to live is like it expires, it already expired. Then you drop the
it
package.
doesn't get to host again.
Yeah, so you can send the TTL package, but of the reset. So like the reset thing, the reset packet that drops the connection, such that the TTL is smaller than the time that the sensor receives, but larger than your receiver. So your sensor receives this packet and thinks that this packet is still alive, and so it drops the connection. But the receiver receives the packet and the packet is not alive anymore, it expires, and it doesn't drop the connection.
Why it is bigger?
What do you mean by bigger?
The other way around.
Yeah,
It should
I
be
was thinking the same
smaller
thing.
than your
So-
destination, but larger than.
No. Why a receiver?
So it
is-
needs to not expire for the
I understood. I mean,
time to live is like the day to expiration,
Yeah, but
right? Oh wait, I need to swap them, right?
yeah,
I don't
Oh yeah, I need to
I
swap.
am
Sorry. So the sensor is here. So when
I understood the idea anyway.
yeah.
Also maybe drop the equals on one side.
Is it important?
So it's simple.
We'll just figure out the TL of sensor exactly how it's going to be.
And do an asymptotic analysis.
Yeah, I thought this is genius. Of course, we can't reliably set the TTL such that the sensor this satisfies, but I guess some papers do this, and in some cases that works.
Well, I guess it's trivial to figure out it dynamically.
Yeah. Also, for context, let's jump from Geneva to something. I saw a paper called AMOBA. It's the same thing, but with reinforcement learning. The thing that they do bad is assume that a sensor is a neural network, and so they train with they train their own sensor basically, and train the reinforcement learning algorithm against that. But the interesting thing is that their set of actions is different. So what they can do is they can change the packet sizes and they can change the interpacket delays. So this is what their algorithm changes. So, for example, the neural network receives a packet with a particular, like a sequence of packets with particular lengths of these packets, and the neural network can predict like whether to cut those packets or to extend them or like pad them with whatever strings, and also whether to introduce some delays between sending these packets. So this is what neural network predicts, which is a lot like it's interesting. It's completely different from what Geneva does, and apparently that works too. So Geneva does not introduce any interpacket delays or tamper with the time at which we send the packets, but this one does tinker with that, and it works.
So I'd say that this one operates in a kind of different framework. So this is the sort of thing you would see in mixed networks like Tor or something, where like an interpacket delay is kind of the delay that you can take when the packet is routed between different hosts, and the paper we started with Geneva is more like this play with bits to try to cover a particular protocol. So this what I'm saying is that this would actually combine. So like when you have Tor these days, you can if you're in a censored country, then you would run Tor over some bit twiddling algorithm. And actually, if you're curious, I looked up to see if Geneva is used in the wild. Apparently, it's not, but I could like give a short survey of what is. Actually, yes. I mean, the reason I have to just censorship prevention with the technique is I have no idea.
I mean, on the other hand, do you need to kind of use Geneva constantly, or you kind of run it once,
censorship.ai,
or even several algorithms, and then just implement these algorithms, and then you avoid censorship at least for some time in the future while they.
Oh, it redirects to this website.
They made the company already.
Oh, it's like a project page for the paper. Real
Looks like a
world
company
ones.
like.
Yeah.
Oh, they do a bunch of research.
Oh, I guess it's like a
A working
page of
group.
a university lab
Yeah.
with a landing page of this paper.
Isn't there also
Yeah, so they apparently have like a bunch of research deployments, but not widespread use, you know.
And what do you think? So I have this horrible question that come up when I listen lecture. If this is open sourced, all of these papers about censorship, bypassing censorship mechanism, it is. Can Chinese government read this paper also and make
Of course.
a different algorithm that will fix this kind of techniques
Of course.
with bit shiftings, and in this way, for example, they can improve censorship in like that. So you can't bit shift a lot because this system will identify you as a neural network, for example, as a train to investigate censorship itself, and will drop forever, not for 90 seconds, these packets, and for example, block this client from internet at all, and somehow like that.
I mean, if you do these kind of radical blocks, I think they will get too many false positives.
So it's done in Russia, so someone just put IP addresses, random IP address on their problematic DNS, and everything was blocked.
Yeah, like so something, everything with the letter M in the domain, something like that.
I don't remember. Some Russian government sites were blocked because of this. Because some
Yeah. And so
website decided to put
If we block too radically, then we will get a lot of false positives, so blocking when there's actually was no forbidden content. And that's bad for the party because it makes the party look bad, they're too disorganized and stuff
So
like that.
it's impossible to create, for example,
I think it's easier just to block some
so
terrible packets.
can we train another neural network that will try to detect neural networks
Of
that's
course.
trying to attack?
We can try to, but again, like it's easy to change this to add like some other types of actions that these actions will be introduced to the action tree, and so new ways to adapt to new like censorship systems. So again, as the introduction said, it's always a cat and mouse game, as with spam and spam detection and stuff like
I
that.
think it's just easier to block very corrupt stuff going to through the sensor.
But most of these things are not corruption. There's they like just inject a new TCP packet that for some reason like confuses.
It's very strange.
Like you
To
can,
block.
they literally just copy the message, change the flag, and it already like breaks everything. Even though like the payload message, the checksum is all lines up, but like some combination of this will confuse the system.
So I'd say the key insight here is that the game is asymmetric in a sense, as in the sensor has to process like terabytes of data per second, and that's why they do this sort of like optimizations.
I remember when I was in China, Stack Overflow page was opening for me.
Yeah.
It's long.
Yeah.
They do stuff probably there.
Actually, one censorship strategy to avoid false positive kind of is to not drop traffic totally, but just throttle it. So like you don't drop Stack Overflow, but you only give it like 100 kilobytes per second pipe, and like.
I know.
But then you need to.
I was watching one month recently, and he was saying that in Eritrea internet is too slow, and nothing makes sense at all to do because YouTube will not just work at all because it's too slow.
But also, like throttling connection means that like they have to have a man in the middle, right?
They have to maintain more state, yeah.
So they need to force ISPs to introduce this.
Yeah. So more expensive, yeah. So yeah, I think like the key insight of these sorts of techniques is that sometimes you can cheaply exploit the asymmetry of the game and like make censorship more expensive, which you're going to pay for with your taxes, by the way.
And why they, for example, not creating a tool with closed source, and for example, they will publish Geneva like a tool, so you can download it, but you don't know what inside. So
I mean, of course, lots of papers. Not papers, I guess. There's probably lots of hacker communities that do this sort of stuff and just don't publish papers, don't like share their findings. Like it's literally survivorship bias, yeah.
Oh, okay.
I mean, Wireshark will open all this stuff probably. You just send small packet and watch what's going on.
Yeah, so you can see that this tool doesn't know what the sensor is doing, but it figures it out anyway. And the sensor can do the same. It can just run it in the lab and inspect the traffic and fix the bugs it found.
Yeah, I don't have any other stuff to tell you.
I think it seems to me like the key part of this paper is this set of actions they found.
Yeah.
Do you know how they came up on it?
I mean, they say that they like come up with this as like a very. I don't know where to find this. They said like it's a small set of actions that is small and it represents most of the research into censorship evasion.
Like, they read a bunch of papers and tried to like
like a general thing that can represent all of them, but also is like pretty compact.
Okay. Yeah, I think that's maybe like the best contribution here.
Yeah, it's simple. It works. Okay. Yep. Let's get the stage to the next speaker. I guess.
Yeah, maybe take a break.
Yeah,
also, if you like, I can like give a 4 minutes long introduction to like currently used widely censorship.
Yeah.
Censorship evasion techniques. Okay, then I need the. So this is just for a few minutes, an extended comment sort of. So like, if you want to know one thing about censorship evasion, learn this pluggable transports. It's a project by Tor and a bunch of other folks in the space, which basically defines a simple interface which people can implement, and like it's an umbrella project with a bunch of research and a bunch of ideas implemented in code used by censorship evasion projects, which are, I think, mainly again Tor, but also I'm not sure. Didn't keep up to date, but yeah. So pluggable transports, a bunch of projects out there, and I'd like to just run through the few ideas which are used by them in practice. So like idea one, domain fronting. Goes as follows. You have, say, Cloudflare. Cloudflare is good, as in you can't block Cloudflare because many good sites use it.
You can buy Snai.
Yeah, but what we can do here is we can send like at the lower protocol level we can send like good website data. Yeah, but in unencrypted HTTP host, we can send bad website data and have Cloudflare proxy the right way for us. So that's domain fronting. We can also do this with like Google Cloud, Amazon Cloud.
Yeah, something like steganography where we hide data instead of
Yeah, kind of steganography, but on a proxy level, if that makes sense. Okay, so another idea is WebRTC. So WebRTC is basically send arbitrary binary data to the website sort of protocol, which you normally use for video conferencing or this sort of stuff. And like this project here is piggybacks on it to build a kind of proxy hive. So like when people connect to a website, they become proxies in turn, and WebRTC is normally not blocked because it's normally encrypted and doesn't bear plain text metadata, so like not much to block there.
Yeah, I think it's worth mentioning that actually WebRTC is peer-to-peer.
Oh yeah, thanks for that.
Yeah, that's why kind of you turn visitors into this type of proxies, because they start messaging peer-to-peer,
Yeah.
browser to browser.
Thanks.
Directly.
So this is again like kind of steganography. This is more like streamed, usually used for video, but it can be used for exchanging arbitrary binary.
Yeah, but and also it has peer-to-peer mechanism built in. Yeah. Okay, so next idea, it's kind of weird. I didn't even understand what they're doing at first. So like, this needs cooperation from another network provider, maybe in a different country. So what you're doing here is in a browser, the user requests a blocked website. The browser has an add-on which rewrites a blocked site to some other website. This other website is okay, so sensor passes it through. The ISP which hosts the good site sees this request and forwards it over to the block site. How's that?
Wait, again.
Okay, so we request a good site. The network provider which hosts the good site redirects our traffic to the bad site.
And how do we do that? So is ISP? So I, as someone who wants to use this censorship,
Like,
do I need to make an agreement with some kind
Yes.
of ISP?
but apparently ISPs in liberal democracies are very willing to sacrifice the sovereignty of authoritarian governments in terms of information and stuff like that. Yeah, so that's refraction networking. This is something pretty new, I think. Okay, the next thing is OBFS4. It's the current state-of-the-art protocol used by Tor for evasion. And what it basically does is make your traffic look like random bytes on the wire. So like encrypt and chunk in a particular way.
Really? So does it look like? Does it make your bytes look like random or like legit?
Like random.
That's
So you need to
not
work
really-
random
I
bytes.
think, yeah. Now
Yes.
they kind of crack on random.
I mean, yes.
Yeah, people start developing these techniques to make
Uh,
it look like legit.
Yes, which is exactly why we have the next protocol here, to statistically match a pattern of allowed traffic. And then we have lampshade. I think I don't have a concise explanation of lampshade, unfortunately, but well, lampshade is kinda sorta like recent build-ons on shadow socks, like V2 or something. So like a thing which tries to look like nice HTTPS and also a few tricks, like it's a paper on its own. I'm not going to go into it here. And then we have an optimizer, which is pretty straightforward. I think I have it yeah, here. So actually very bare bones. So like either rotate the transports or choose a random one for each request, or track which are good and use those, or take one which connects fastest. So yeah, right, straightforward. You can just orchestrate the ones which we walked through with this sort of like meta transport.
And then you need to protect yourself from active attacks by a proxy.
I mean, you can just do that if you if your data is signed and if you want to protect against editing by proxy, then you just sign the data. If you want to protect against dropping by proxy, then you send it over multiple
I mean,
transports.
some CSP, how it's called, just connects to your proxy and check what's going here. Is it really the website?
I see.
And like you just always get some squid error or something. It's,
yeah,
not squid, but
but like notice that what we're doing here is we're again like raising the bar, making it more expensive to check that.
It's not expensive just to go to the website, actually. Especially for some. We're always checking this Chinese firewall, right? Other firewalls are usually okay with stuff.
But like consider the scale. So like how many checks do you expect to have to make per second?
Chinese firewall can do a lot of stuff randomly.
Yeah,
According to what I heard.
I mean, I don't know.
Other firewall sucks anyway. What's the difference?
I think, like, I think it's useful to think about this quantitatively. In that, why aren't we talking about the government making everyone use their HTTPS certificates only and blocking all encrypted data? Why aren't we talking about that?
What?
What do you mean?
I mean,
What do you mean by talking?
I mean, like, for any particular technique, you can raise the question, why doesn't the censor just circumvent this technique? And I'm asking, why aren't we talking about the case of the government blocking all encrypted traffic totally?
They're trying.
Well, I think that's the case for China, yeah. And they pretty much do that.
They don't do
Okay, so
For what I heard, they pretty much.
I was in China and HTTPS was working.
all right, so maybe let's take the question another time. Now let's take a break for a few minutes just to stretch our legs and then go with the next talk.